Hi guys, welcome to lesson 7.3 on using functions involving e. Today we're going to be talking about studying functions that involve the natural base e. And what is e? Well, the natural base e, so you'll notice that we never used e as a variable, and the reason why is because e is actually a constant. All right, much like pi is a constant. That's 3.14, etc. All right, e is actually a constant, which we'll get to the value of that down here in just a few minutes here. But the natural base e is some irrational number. Again, irrational means non-terminating and non-repeating, where 1 plus 1 over n to the n power approaches e as n increases. So as we take n goes to infinity, all right, this function here, or this expression, moves to some arbitrary number e. And again, that e is a constant that we'll use mathematically throughout the course of the rest of this chapter and further, okay? All right, so the natural base e is this irrational number, and again, as n approaches positive infinity, this expression right here approaches some number, and you guys can play around with that in your calculator if you want. You can do 1 plus 1 over like 5 to the 5th power, and then to figure that out, 1 plus 1 over 6 to the 6th power, 1 plus 1 over 7, all right, to the 7th power, and go way up to like 1 plus 1 over 100 to the 100th power, and you're going to get something that's going to start approximating this 2.7-ish number, which that 2.7 number we refer to as the natural base, which is e. All right? So if I asked you the value of e, you should be able to tell me up to about 3 decimal points. It's about 2.718 roughly, and again, that value is going to never change. It's going to be a constant value. All right? So let's talk about simplifying some natural base expressions. Again, this e is, we can kind of treat it like a variable if we want to, but really this says two things with the same base. What do we do to the exponents? Well, that's 6 plus 3, so this is e to the 9th power. So again, just to review on your exponent properties, when we have two things with the same bases, we add the exponents. Okay, what about this guy? This is 18 divided by 2, which is 9, and this becomes e to the 6 take away 4, which is simply 9e squared. Now the next one, again, because we're squaring everything, this becomes 4 squared e to the 3x squared. Well, 4 squared is pretty easy, that's 16. All right, and then e to the 3x squared, okay, again, we multiply those exponents, this becomes e to the 6x power. All right, let's go ahead and evaluate a couple things on your calculator, because I'm going to want to show you where that button is on your graphing calculator. If I take a look over here at your grapher, the E key is, if I press the, well, let me circle it for you first. Your E key is above this LN button. We're going to talk a little bit about LN in a couple more sections here, but that LN button, to the top of it, you'll see that it has an E to the X power. All right, so if I want to get E to the X power, I have to go second E to the X. Whoops, I must have missed the second. Let's try that again. Second E to the X, there we go. And if I wanted to know what E to the negative 2 power is, okay, that comes out to 0.1353, etc. All right. Notice that when the exponent on e is negative, keep in mind what that does for us, guys, is that really means 1 over e squared. And since this number here is like 2 or something like that, 1 divided by 2 something is something that's less than 1. Okay, it ends up being 1 divided by 2.7, you know, 2.72-ish. All right, and that's obviously a number that's less than 1. That's going to come into play in just a few minutes here. So when that exponent's negative, keep in mind that e to the negative power is going to end up being something that's less than 1. All right, so e to the x, and then it automatically puts this in for you. We have to type in negative 2. You don't have to really put the end parentheses in there if you don't want to. You get roughly 0.1353, etc. Okay, that's good enough for me. How about e to the 0.3? This is e to the 0.3 power. And again, e to the 0.03 power ends up being something like 1.34985, etc., etc. All right? So again, if you want to see how we would do that, we would take that second e to the, whoops. There we go. Second e to the, and we would put to the 0.3 power. And again, because this is being raised to a positive number, e to a positive number is going to be something greater than 1. Like like I said, that's going to come into play. Keep in mind that 0.3, while it's less than 1, it's positive, and so e to that power right there is going to be a number that's more than 1. Okay? All right, so let's just try a couple of examples, the checkpoints here, a couple where you have to simplify and a couple where you actually have to do some calculator things here. But go ahead and give this a shot. Before you plug these into the calculator, try to do them without first. All right, so if you simply plug this into the calculator, you're going to get a decimal, which is not what we want. We want this as e to the negative 3 plus 6, which becomes e to the third power. All right, in the next example, keep in mind we're squaring everything, and so this becomes 4 squared e to the 6th power, because 3 times 2 is 6, all over 8 e to the 5th power. All right, now, 4 squared is 16. 16 divided by 8 is 2. And then e to the 6th over e to the 5th becomes e to the 6th take away 5. And that becomes just e to the 1st power. So the answer for that one is actually just 2e. What about this guy? Remember, this means 1 over e to the 4th power. We're not going to worry about that, but I know that this is going to be less than 1. So when I plug that into the calculator, I get 0.0183. And in this case, again, this is now e to the 0.36 power, which is approximately 1.433. Again, if you need some help on plugging in those buttons, we can talk more about that tomorrow. Okay? All right, so let's look at natural base functions. Natural base functions really have a little bit to do with this idea. It says a function of the form y equals a e to the rx is called a natural base exponential function because the base is e. So since the base is e, and obviously we said e is the natural base, then this is called the natural base exponential function. If the initial value, a is greater than 0, and r is greater than 0, meaning it's positive, okay, this is that exponent we just talked about a few minutes ago. If this is positive, the function represents an exponential growth, okay, because the base is going to be greater than 1, which means it's going to be exponential growth. If the initial value is greater than 0 and r is less than 1, meaning like e to the negative 2 power like we just did, this is going to lead to exponential decay because, again, the exponent's negative, which makes it 1 over e squared, which this number is less than 1, and so therefore my base is less than 1, which leads to decay. All right, so let's take a look at a couple examples here. Let's graph a natural base function. Let's start with y equals 2e to the 0.6x. All right. Now, since a is equal to 2, and that's a positive number, and in this case the r is equal to 0.6, and that's also positive. Okay, the function is going to be an exponential growth function. All right. So when I plug in 0, again, when I put 0 into this, this is 0.6 times 0, which the whole thing becomes 0. Anything to the 0 power is just 1. So this becomes 2 times 1, which is 2. So once again, this value a is still my initial value, just like we talked about in the last 2 sections. All right. When I plug 1 into this function, I end up getting like 3.64. You guys can do that on your own. You can plug this into your graphing calculator and use the table feature. Again, you can just plug that value of x in there, x equals 1, and so this becomes 2e to the 0.6 times 1, which is 0.6. So you could do 2e to the 0.6 power, and that comes out to be 3.64. In either case, however you do it, it doesn't matter, but that's 3.64. So let's go ahead and plot those points. 0, 2 is here. 1, 3.64 is 1, 2, 3, 4, so roughly right in there. We know that we have exponential growth, so my asymptote is going to be right here at x equals 0. So my function over here is going to get really close to that, and then I'm going to kind of turn the corner and head somewhere like that. And again, you can always get a picture of that if you want to use your graphing calculator too. The domain in this case is all real numbers because you can take any number. All right, you can take any number and do 0.6 and then raise e to that power. And the range is y has to be greater than 0. Again, not greater than or equal to, just the values of y that are bigger than 0. All right, so I'm going to clean this up a little bit. Let's go ahead and take a look at the second example. All right, now in the second example, let's see if I can see both. I don't know if I'll be able to see the function. All right, looks like I can kind of get it there. There we go. All right, in the second value, in this case, a is equal to 1 because there's a 1 out in front of here, and that's positive, right? And r is negative 0.35, and since that's negative, this is going to represent exponential decay. So that says as x goes to infinity, my function is going to try to get to 0, but it's not going to quite get there. So let's go ahead and graph the parent of this. Let's forget about the +1 and the -2 for just a second. Let's graph the parent, y equals e to the negative 0.35 to the x power. And so again, as I take a look at this a little bit, we need some values for this thing. So let's look at this guy right here, and let's get some values. When x equals 0, this becomes 1 times e to the blah, 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 all that to the 0 power, which simply becomes a 1. When x is equal to 1, I get about 0.704, and so 0.7 is probably close enough, and then so on and so forth. So let's go ahead and graph that. Here's the 0.01, kind of missing it there. And then 1.74 is going to be kind of like down in here somewhere. And so again, because this is exponential decay, it's going to kind of work that way like that. All right? Now, because of the +1 up here, that's going to move this thing to the left 1. And because of the -2, it's going to move it down 2. All right? And so what we want to do then is let's pick a different color here. All right, and so now because of the +1 and the -2, that's going to take each of these points and move them down left 1, so left 1, and then down 2, which is roughly right in there somewhere. Not quite hitting it, but that's the idea. And then left 1, which is down here, and then down in here somewhere. In any case, you should get something, again, because this is -2, that moves our asymptote down to -2, and so my graph's going to look something like this. All right. The domain of this thing is, once again, all real numbers. And the range is y has to be greater than -2, because since this moved it down 2 units, I have to be above -2. All right, top of the next page is a checkpoint problem for you guys. Why don't you give that a shot for me? And we'll be right back with a solution. All right, let's examine the parent first. Y equals 2e to the 0.7x. Once again, this is positive and this is positive, so this is going to be exponential growth, all right, because a and r are both greater than 0. They're both positive. All right, so that's going to give me exponential growth. Again, forget about the +3 for just a second. Let's make a table for this guy. When x equals 0, y equals 2, because again, this is my initial value. Always, when x equals 0, y is going to be equal to a. When x equals 1, I end up getting about roughly 4. Again, it's 4.0 something or other, but I'm just going to leave it as 4. And so the 0.02 and 1.4 is roughly in there. Again, this is exponential growth, and it looks like it, right? We're going to take it something like this. And let's switch up colors here now, and let's go ahead and graph the other. Now, because this doesn't have anything affecting the x, it's not going to move left or right. It's just going to take all those values and move them up 3. All right, and so here was my original point. I'm going to go up 1, 2, 3, and I'm going to go up 1, 2, 3. And so my new function is going to look something like this. But before I continue with this, keep in mind that the asymptote should be moved up 3 because it used to be at 0. So 1, 2, 3. Here's my new asymptote at y equals 3. And so that means as I go to the left, my function should get really close to that, but never actually reach it. All right? All right. The last piece of new information for this lesson is this idea of compound interest. And we talked about compound interest before, back in section 7.1. We said this is y equals a times 1 plus r over n to the nt power. Now, as the number of compounds go to infinity, you know, we can compound 365 times a year. That would be daily. We could do it 2 times a day, which, again, you know, we can continue to increase this value of n. But if we continuously, around the clock, every second of every day, even more than that, compound the interest, our function ends up kind of going to, and again, remember we said that this thing is 1 plus r over n to the n power, and as this goes to infinity, as n goes to infinity, this thing approaches e. So effectively, this thing becomes principal times e to the rt power. All right? Significantly different and much more simple than this guy, right? But in this case, we're compounding continuously, and that's the big key here. We're compounding continuously. That means around the clock, every single day of every single hour, every single second, we're compounding interest. All right? Again, p is the initial value, my principal. and then R is the interest rate, annual interest rate. Most of your banks compound interest monthly, typically not daily, but there are applications where we compound continuously. And so let's take a look at a few examples of that. All right, sliding on down here, it says you deposit $3,500 into an account that pays 4% annual interest, compounded continuously. Keyword there is continuously. So that tells me I'm using my PE to the RT formula because it's continuous interest. All right. What's the balance after 1 year? So this is $3,500, and then times e to the RT power. Well, my R is my interest rate, which is 0.04, and that's times t, which is we want 1 year, right? All right, because we want 1 year, and so I'm going to plug in 1 year here. All right. When I plug all that in my calculator, again, 0.4 times 1 is just 0.4, e to the 0.4 power, and then times 3,500, you end up getting about $3,642.84. And so my balance is roughly $3642.84. Now, if you did that same example with 4% interest compounded yearly, we would not nearly get as much money because our compounding interest, the more times we compound, the more frequently we compound, the more money we get. All right? Let's go ahead and try the checkpoint problem on your own. Let's see how we do. All right, so let's talk a little bit about some money here. Your amount is equal to your original principal. Again, because it's continuous interest, that's PE to the RT power. So it's $4,800, e to the interest rate of 0.065, and we want to know what's the balance after 3 years, and so it's 3 years. All right, plug all that into your calculator, 0.065 times 3. Raise e to that power, you end up getting roughly $5,833.49. All right, that concludes our lesson on 7.3.